So welcome one and all. In today's lecture we will discuss some more problems in Bernoulli. So in the previous video we have seen the Bernoulli's differential equations in which y is a dependent variable and x is an independent variable. Now in this video we will see if x is dependent variable then and y is independent variable, then what is the general form and how to solve that. We will see that one with the help of one example also. So first of all, let me write the general form here for Bernoulli's in the first order. Dx by dy plus p of y into x is equal to q of y into x power n. So actually if it is linear in Bernoulli's in y is independent and x is dependent, if y is dependent and x is independent, then we get dy by dx plus p of x into y is equal to q of x into y power n. But here x is dependent and y is independent, then in this case the general form is given as dx by dy plus p of y into x is equal to q of y into x power n. So here also we will follow the same procedure as we did in the previous case also. So first of all you multiply with 1 by x power n on both sides. Okay, multiply with 1 by x power n on both sides. The equation 1 now then reduces to 1 by x power n into dx by dy plus p of x into p of y into p of y into x power 1 minus n is equal to q of y. Now here also we have to convert this one into linear, that is our aim. So for that we have multiplied with 1 by x power n. Now here you replace, so that x power 1 minus n with some t, okay, and if you find the derivative for this, then we will get 1 minus n into x power minus n into dx by dy, because here the independent variable is y, is equal to dt by dy. Here we will get, otherwise here what we need, x power minus n into dx by dy only we need. So that's why now we can write it as x power minus n into dx by dy is equal to 1 by 1 minus n into dt by dy. So if you substitute all this, means this is one equation 3 we have to take the help, and this is the another one. So if you substitute these equations 3 and 4 in equation 2, then that equation now reduces to linear in t. Okay, now we will see. Now if we replace all these things, so first of all we will replace this term, so that is nothing but 1 by 1 minus n into dt by dy plus here p of y into x power 1 minus n, means what we get, p of y into x power 1 minus n now can be written as t only. Okay, so that x power 1 minus n now we can write it as t. So t is equal to, right side as usually whatever we have we will write it as q of y only. Okay, now if we simplify, we can write dt by dy plus 1 minus n into p of y into t is equal to 1 minus n into q of y, which is a simple simplification. So if you want, you can replace this one with some p1 and this one with some q1. Otherwise also no need actually. Otherwise to observe this one in some particular standard format. So if you want, you can do it like this, where this one is p1, 1 minus n into p of y, and 1 minus n into q of y we had taken it as some q1. Okay, now this is nothing but dt by dy plus p1 of y into t is equal to q1 of y. Now this is nothing but linear, so which is linear in t. Now we know how to solve a linear differential equation, so therefore for that now we have to find out the integrating factor given by integrating factor is in power integral of, here what we have, so the coefficient of t is nothing but p1y, so therefore just we have to write p1y dy. So by this we can find out the integrating factor, and the general solution for 5 is given as, we can write it, the general solution of equation 5, because equation 5 is linear, is here the dependent variable is t, then we can write t into integrating factor is equal to integral of integrating factor into, so here instead of q, here we have q1, so q1y into dy. So this is nothing but the general solution of equation 5, but we need the general solution for the given equation, means now we have to replace what is this t. So t is nothing but, here we have taken x power 1 minus n, so here if you replace t by x power 1 minus n, so then we will get x power 1 minus n into integrating factor is equal to integrating factor into q1 of y, so means q1 of y dy plus c, where c is nothing but the arbitrary constant, we can write like this. So now this is nothing but x power 1 minus n into integrating factor is equal to integral of integrating factor into q1 of y dy plus c. Now this is nothing but the general solution of the Bernoulli's differential equation, where x is the dependent variable and y is the independent variable. So this is how we can solve this. Okay, so here if you want, without converting like this, by using this directly also we can find, because here p1 of y is nothing but 1 minus n into p of y, means the integrating factor directly for the given dE we can write integrating factor is nothing but e power integral of 1 minus n into p of y dy. Similarly here also, instead of this q1y if you replace this q1y with 1 minus n into q of y, and then directly also we can find out the solution for the Bernoulli's differential equation in this standard form. Now we will discuss this with the help of one example. Okay, with the help of one problem we will see now. So now we have a problem like this: sum dy by dx into x square y cube plus xy is equal to 1. Now we will see how to solve this differential equation. Okay, now first of all we will try to put it in the standard format. Now just you observe whether we can write like this. First of all you simplify, multiply, so dy by dx into, so instead of doing like this, so if you write it in the form of dy by dx actually, then we cannot simplify this. So that's why better you write it in the form of dx by dy, so that we can easily simplify and we can separate the variables. So means now we can write it as dx by dy. Dx by dy is equal to x square y cube plus xy, we can write it. Okay, now you bring it to the standard format as we have discussed in the previous page. Now you can write it as dx by dy plus xy is equal to y cube x square. Now it is in the standard form of dx by dy plus p of y into x is equal to q of y into some x power n we have. So take the given differential equation as 1, this one as 2. Now equation 2 is Bernoulli. Equation 2 is Bernoulli. Okay, where the dependent variable is x we have. Now you divide on both sides with x square. Okay, otherwise multiply equation 2 on both sides with 1 by x square, then we get 1 by x square into dx by dy plus y into 1 by x is equal to y cube we get. Now is it linear? So no, it is not at linear. Now here what we will do is you replace this 1 by x with some variable. So now you just replace, put 1 by x is equal to some, introduce new variable t. Okay, now we just find the derivative of 1 by x is minus 1 by x square into dx by dy is equal to dt by dy. But here we need, what we need here, 1 by x square into dx by dy only we need. Okay, so that we will see how to eliminate. Just you simplify this, in the sense just you write like this, dA 1 by x square into dx by dy is equal to negative of dt by dy. Okay, so if you substitute 1 by x is equal to t and 1 by x square into dx by dy is equal to minus dt by dy in equation 3, so then equation 3 changes to or transforms to or reduces to whatever it may be, equation 3. So 1 by x square into dx by dt can be written as dt by dy, okay, plus y into, in place of 1 by x we have to write t is equal to what we have on the right side we have y cube. Now if you observe, take this one as some equation 4. Now if you observe this equation 4, dt by dy plus y into t is equal to y cube, it is nothing but a first order linear differential equation in t. If you want you can write it. So equation 4 is linear in the variable t. Okay, now we know how to solve a linear differential equation. So first of all you will take the integrating factor. So therefore, so once if you identify this is linear in t, so therefore the integrating factor of equation 4 is if is equal to e power integral of, what is the coefficient of t here we have, y into dy. So this is nothing but e power integral of y means we have y square by 2. So that is the integrating factor. So now we will write the general solution. So and therefore the general solution of equation 4 only we are going to calculate, because we have identified that 4 is the linear in t. So therefore the general solution of equation 4 is in the form of, okay, so what we have, t into, because t is the dependent variable here, t into integrating factor is equal to integral of integrating factor into what we have on the right side of the equation 4, y cube we have. Okay, you write it here, y cube into dy, and of course the integral constant or the arbitrary constant c we can write it. Okay, now that implies t into, so what is the integrating factor here we have, e power y square by 2 is equal to integral of, integrating factor is e power y square by 2 into y cube into dy plus c. Now we have to evaluate this integral. So if you can write directly here we can write it, or otherwise you just replace this y square by 2 with some p. Okay, now introduce with some new variable, y square by 2 is equal to some p. Now we can write it, implies 2, if you find the derivative 2y dy is equal to dp. So 2 cancels out and we will get y dy is equal to dp here we will get. So if we substitute all these changes in this integration, then we can write it here e power integral of e power y square by 2 can be written as p. So what else remains here? Y cube remains. So this y cube can be written as, y square into y. Okay, so this y dy can be written as dp, and remaining y square can be written as here from this, what is y square? Y square is equal to 2p. So this y square into y can be written as 2p, because y square is 2p, and y dy can be written as dp, we can write it. Okay, now this is equal to 2 into integral of p into e power p dp here we have. Okay, now it is of the form of integral of x into e power x. If you want, you can apply integrating by parts. Then the direct formula you can write integral of x into e power x is e power x into, so e power x into x minus 1, in the sense e power p into p minus 1, we can write it. Okay, plus c already we have. Okay, now finally we will see how it is. So left side we have t into e power, and right side we have something like this. So then finally we have that t into e power y square by 2 is equal to what we have on the right side. Let me check it once. 2 into e power p into p minus 1. 2 into e power p into p minus 1 plus c. So p means we know that is nothing but y square by 2. So t into e power y square by 2 is equal to 2 into e power y square by 2 into y square by 2 minus 1 plus c. Okay, now this is nothing but, if you want e power minus y square by 2, if you multiply on both sides, then we will get t is equal to 2 into y square by 2 minus 1 plus c into e power minus y square by 2, we can write it. Of course, where c is an arbitrary constant. So this is the general solution for that linear differential equation in t, means that is the general solution of this differential equation 4. But we need the general solution for the given d, means we have to replace t. What is t here we have taken? T is nothing but 1 by x here we took. So means that is nothing but equation 3. Now here we replace that one in the final solution. Then we get t is equal to 1 by x. If you replace, then we will get 2 into y square by 2. If you want, you can simplify this one also, minus 1 plus c into e power minus y square by 2. And if we want, here you can write since from equation 3. Otherwise here if you want, you can replace this or simplify this. So 1 by x is equal to y square minus 2 plus c into e power minus y square by 2. So this is nothing but the general solution of the given, so which is the general solution of the given differential equation 1. And this is nothing but the general solution of equation 4, which is nothing but linear in t. So after getting that one, just we have to replace what the value of t, and here we have taken the value of t as 1 by x. So if you replace that, and if you go for the simplification here, then we'll get 1 by x is equal to something. So this is nothing but the general solution of the Bernoulli's differential equation, which was given something like this as dy by dx is something, and here especially the specialty of this problem is this is the Bernoulli differential equation in x, in the sense x is the dependent variable and y is the independent variable. So this is how we can solve the differential equations in Bernoulli's. Thank you one and all.